So my name is Yishay Carmiel. Actually, the title of the talk of Future is Speech Understanding or Voice Interfaces, but it's exactly the same. And before I start, a little bit background about myself. So I've been working on speech for almost 20 years now. And I've been starting working on deep learning since 2012. And I'm always joking in my talks that until 2011, I was one of the weird guys because we were working on all these algorithms and they're not working so well. And then I became one of the cool guys because I started to say that I'm working on deep learning, which is pretty cool. So I want to discuss a little bit about the future of speech. Yeah. And the first question that I want to address is why speech is interesting. And the answer for that is, first of all, because it's working. And let me start with a few statistics, is that according to ComScore, by 2020, 50% of all searches will be based on voice. And according to Gartner, 30% of all searches by 2020 will be on screenless. And I'm living in Seattle, and actually in Seattle and also in the Bay Area, and in the US, Amazon Echo and Google Home are products that are being sold by tens of millions. And the second question is that why Amazon Echo and Google Home are so disruptive. And the answer for that is that they represent the next evolution of search. And if you are thinking about it, if you are thinking about search, when search started in the desktop, so we had companies like Microsoft and Google who build, products to capture the search market share, for example, browsers like Google Chrome and Internet Explorer. Then when search moved into the mobile, we had, the iOS and versus Android battle. And now search is moving into what we call the ubiquitous computing. And Amazon Echo and Google Search and Google Home are actually representing the next evolution of search. So the company who will win in the real estate of conquering that will win the search. But if you are thinking about it, when we are thinking about voice search, we are just scraping the tip of the iceberg in terms of what we call voice-based applications. And when we are thinking about the first type of application is what we call man-machine interface. When you have human on one side, you have a machine on the other side, and the human is interacting with the machine through voice or text. So machine can be Amazon Alexa or Apple Siri or Google Home for the matter of fact. But if you are thinking about it, 95% of the time, and actually that was in the talk before me, is that we're not going to talk with machines, we are going to talk with other human beings. So one of the things that is really interesting in analyzing, voice is analyzing human conversations. And one simple example is, think about conference calls. So I bet that a lot of people in the audience really love conference calls. And I see a lot of smiling faces because nobody wants to be that guy who is writing the summary or doing all the follow-ups. So think about if you had some kind of, what they call Siri on steroids that just sits in the middle and transcribe everything and create some kind of a summary and doing all the follow-ups. So that's one application of voice when analyzing conversations. The second type of, for example, think about the patient going to the doctor. So today the doctor is, really paying attention, sometimes not to the patient, but just writing, the information, writing the electronic health record of what's going on. Think about if we had some kind of an Amazon Echo that sits in the middle, listens to the conversation, and assists the agent, or in the case, the doctor, to fill out the relevant forms. And when we are thinking about it, there are two types of voice interaction. So as I said, the first is what we call human-to-human interaction, and the second type is man-to-machine. But they can come in the form of what we call dialogue or a monologue. And today, if you are thinking about it, when you are talking to Alexa, I know usually most of the things that we are thinking is just some kind of a very, very simple state machine. Hey Alexa, play me Lucy in the Sky with Diamonds. Hey Alexa, what is the weather in San Francisco? But Amazon, I'm based in Seattle, and I see that these big companies are putting not millions of dollars, like tens of millions of dollars, and more than that, to create something that we call the dialogue. That you can really create some kind of an interaction or what we call task completion with Alexa or Siri. And when we are talking about human to human, everything is a dialogue. But one important problem that is coming when we are analyzing conversations is a phenomenon that is called spontaneous speech. And spontaneous speech, basically, long story short, is that when people talk to each other, they talk really differently than they write. So if, for example, people are looking on speech transcription, it's really unnatural for a human being even to understand what's going on over there. And when we are analyzing spontaneous speech, analyzing human conversation, the classical natural language processing algorithm really won't work. And once we have covered that, so the second question, another question is that with all the breakthroughs in deep learning, with all the cool things that we are seeing, for example, in this conference, have we solved all the problems? And of course, the answer is no. And I'm putting no with an exclamation mark. And one of the basic assumptions, which is not true, is that people think about analyzing humans, that I can build a very, very powerful speech recognition system, add my magic and natural language understanding on top of that, and voila, I can understand humans. The key problem is that so there are a few problems. So first of all, when we are analyzing an output from a speech recognition system, we need to take into consideration that our data has between 4% to 30% errors, meaning that our data is very, very noisy. And when we're analyzing text, when someone is writing something, we can most of the time assume that this data is correct. The second problem is that all of these NLP algorithms are trained on textual data. They're not trained on speech data, on output from a speech recognition system. And as a result, for example, all these algorithms like name entity recognition, part of speech tagging, all of these things don't work. And another main problem is that output from a speech recognition system is an output that we called raw data, meaning that it's not punctuated, not capitalized, and not normalized. For example, you can see John bought 84 bananas. This is the second sentence is the output of a speech recognition system. So that's the first problem. And the second problem is that speech-based applications are not really scalable. And when I'm talking about not scalable, is that one assumption is that speech recognition can solve everything, but the main problem is that speech is really not adaptive. For example, even I'm talking about languages. Speech recognition in Spanish is not speech recognition in English. I need to design a specific algorithm for that. Environment, speech recognition working in a car is totally different than speech recognition working on cell phones. And of course, the application. If I'm building an application to understand, physicians, for example, it will be a totally different application than understanding, for example, people working in Wall Street. So as a result, even if I want to build some kind of an application, I need to do a lot of human work. And right now, one of the biggest problems in speech is how to create some kind of an automation process to that. So, of course, we didn't solve all the problems, but due to deep learning, we are moving in a very, very fast pace. So if you're thinking about deep learning, we can divide deep learning, the impact of deep learning on speech understanding into 3 periods of time. The first is, of course, before 2011, when deep learning was not around. It was before the age of what we call big data and cloud computing. And we were applying very, very sophisticated machine learning and statistical machine learning algorithms, but they were not working so well. And between 2011 to 2014, when deep learning started to appear, we saw some, nice adoption from the big companies like Google and Microsoft, where we saw that, products are being shipped to the market. And in 2015 and onwards, I think that every type of, algorithm that we are thinking about in this field involves some kind of, recurrent neural network or some kind of, deep learning. So let's talk a little bit about the speech recognition. So in order to understand, the impact that deep learning has made on speech recognition, first of all, we need to understand how speech recognition system works. So in very layman terms, speech recognition is divided into 3 main parts. The first part is what we call the signal level, when you have some kind of one-dimensional signal, and we are trying to extract the speech from the signal and to do some feature extraction on top of that. Then the second part is what we call the acoustic level, when we are taking these features and try to classify them into different sounds. And the third part is we assume that this voice is being said by human beings, so we are taking these sounds, combining them into words and into sentences. And the following graph just represents the impact that deep learning has made. So in order to evaluate a speech recognition system, there is a standard metric that is called the word error rate, meaning out, for example, 100 words that are being said by the user, how many words are misrecognized. So for example, and in order to evaluate the quality, there's an industry standard corpora called Switchboard, which I think was recorded in the 1990s, of people having human conversation with each other. And as you can see from the graph, until 2010, the technology was in some kind of a steady state, meaning the error rate were around 23, 24%. And then you see some kind of a rapid improvement. For example, from 23.6 to 5.1, actually today it's 5. And we are talking about almost 80% improvement in the results, which it's not improvement, it's not something it's nice, it's a revolution. And as a result, we see all these amazing products that are being shipped into the market, and actually, even with my really, really heavy Israeli accent, sometimes, these systems works. So we see Microsoft Cortana, Apple Siri. And one of the questions that I'm being asked a lot of the time is, what is the secret sauce? What is the single algorithm that I need to imply to take my system from 23.6 to 5.1? And unfortunately, there isn't a single algorithm. And the reason that there isn't a single algorithm is that, first of all, speech recognition is a really hard problem. And believe me, I know. And the second answer for that is that, because deep learning is so entangled with speech recognition, is that it's a collection of algorithms. For example, if we are talking about the signal level, if we're talking about the speech extraction, today people are using, some neural-based models to extract the speech. If we're talking about the feature extraction, we are using different type of, bottleneck features or convolutional neural networks to create, different type of features. Sometimes, the classical MFCs, or sometimes, these advanced neural-based models. And when we are talking about the acoustic and language level, deep learning is all over the place. And that is why if we are thinking about some kind of an algorithm, it's a collection of algorithms. So that's for speech recognition. So the second part is if you are thinking about the natural language processing. And again, as I said, one of the issues that we need to understand is that speech recognition is just one part of the equation. If I really want to understand humans, I need to apply my magic in the language understanding part. And when people are thinking about natural language processing, it's a collection of problems. We can start from what we call pronunciation modeling, which usually I explained, teaching computers how to pronounce words. And it has a lot of application to what we call graphem to phoneme and text to speech. The second problem, when we're moving from phonemes to words, we have all these word representations and word embeddings, which we are trying to find, similarities between words. Taking words, combining them into sentences, when you have, all these, parsers, part of speech tagging, name, entity recognition, machine translation, that we are trying, to understand what's going on over there. Taking these sentences, combining them into documents, and then there is the holy grail of what we call AI, which is the knowledge discovery, which meaning, given a collection of, or a large collection of documents, can I find information or meanings in this document? And in one sentence, sometimes people ask, what is the secret sauce? What is, the methodology that, that is really made an impact in deep learning on natural language processing? And usually it's recurrent neural networks. And the reason that recurrent neural networks, and it's a very high level, works really well on text and also in speech, is because in recurrent neural networks we have what we call the Markovian property, meaning that when I'm writing a sentence at time t, a word at time t, it has a lot of dependency of what happened in the past. And these recurrent neural networks have, these what I call magical phenomena that they can encapsulate the information that happened in the past and give this information into time t. So in natural language processing, usually there are three main techniques that people are using. And again, it's a very, very high-level term. So the first technique is what we call word embeddings. And when we are thinking about word embeddings, I'm always giving the example of, think about the word cat. So when we are thinking about the word cat, we have, in our brain, we have a lot of meanings. Cat can be an animal. Cat drinks milk. Cat is furry, and sometimes, cat appears in funny YouTube movies. And when we are thinking about, this word cat, we have a lot of, what we call abstract notation, how this word appears. And we're trying to do the same in word embeddings, which we are trying to give some kind of, abstract representation or a vector representation to this word. So that's the first technique. The second technique is what we call sequence to sequence. And usually in sequence to sequence, a lot of problems in natural language processing can be, I want to transform one sequence of words into another sequence of words. Think about machine translation as an example. When I'm trying to translate one sentence in French to English, it doesn't have to be a one-to-one matching. For example, 4 words going into 4 words. It can be 3 words going to 4 words, or 4 words going to 3 words, or whatever. So sequence to sequence, and especially LSTMs in that case, are a very, very powerful technique that was really promising, started in around September 2014, and was really promising until 2016, but it has a very, very main problem, is that in sequence to sequence, what I'm trying to do, I'm trying to encapsulate or to what we call to do an encoding of the whole vector that have of all the information that happened in the past and to encode it into a single vector. And that created a problem because a lot of the information that exists in sentences, I need really to go back to understand what's going on over there, especially in problems like machine compensation, question answering, and for example machine translation. So then in 2016 there was another model or another technique which is called memory network and attention models. And basically memory networks and attention models is that they are trying to create some kind of history of encodings of information, and then I can go back in time. When I'm doing the analysis, I can go back in time and try to find what is the most relevant information that I can use in order to do my inference. So because it's just like 25-minute talk, I cannot give a lot of examples, so I just want to give you some taste for you to understand how things are moving so fast in this field. So basically, when I was thinking about this talk, I said, okay, one of the hottest topics and the hottest problems right now in natural language processing is a problem called question answering or machine compensation. Giving some kind of a sentence or some kind of a paragraph, I want to ask a question about this paragraph. And question answering, can the machine understand what's going on in the paragraph? So this is based on a talk that I gave in March. And in March, I went to what we call the squad. It's called the Stanford Question Answering Dataset. And I just copied the top 8, I think the top 8 or the top 10 results. That was in March. And as you can see, the top 8 results are from the past 2 months. Meaning that these things are evolving in some kind of a rapid phase. They're not that like the most, and I think this problem has been existing around for 3 or 4 years at least. So think about the recent, the 8 best results are just happening happened in between December 2017 to February 2018. So that's amazing. So the second example is, is a very, very important problem in natural language processing is what we call language modeling. And language modeling is I want to create some kind of a mathematical, let's call it some kind of mathematical representation how language is constructed. And usually when I'm evaluating a language model, you can see in the rightmost column is that there is a measurement called the perplexity. And the lower the perplexity, the better the language model is. So this is based on a paper that was from a few guys, recent paper that published in March 2018, a few guys from CMUs. And as you can see, the recent advantage, most of the recent advances happened in 2016 and 2017. So that's amazing. These things are really, really moving fast. And one of the problems for us is just to understand which technique we should apply, because sometimes I'm feeling like a hamster running on a wheel, because every time that you're implementing some kind of a technique, there is another technique in town, and that's a big problem for us. So, saying that, what are the future challenges? And we see that this is really evolving fast, but what are the future challenges? So when I'm thinking about the future challenges, I can think about 3 categories: algorithms, data, and scale. And when I'm thinking about algorithms, so of course we need better models, because today these things are working quite fine, they're working okay, but if I'm talking about really understand people with accents, really understanding in all these environments and all these things, these models are not working well. And we need to improve the models from the speech side and also from the NLP side. And one of the most important things is how we combine them together. Because if we really want to understand humans, we need that these algorithms will work together. The second, of course, is what we call the environment and domain, is that we need to make sure that these algorithms are environment independent, meaning that if I'm creating some kind of an algorithm to distance speech recognition, or if I'm creating an algorithm for cell phones or for the car, hopefully these algorithms will be the same, and I want to redesign my whole system. And today, I sometimes still need to redesign my whole system. The second thing is data. One of the problems with understanding humans is that there is really lack of data, because when you are talking about NLP, just the NLP, there is a lot of textual data that we can find, but there isn't a lot of data to train speech recognition systems, and of course there isn't a lot of data that is an output from speech recognition systems. And because this is a very, very big, complicated data labeling problem, so one of the things that our people investigate today is methodologies like semi-supervised learning or unsupervised learning or generating synthesized data in order to capture better my data. And one of the biggest problems in speech recognition or understanding humans is scaling to new languages. Just for you today, there are around 7,000 languages in the world. And I think that Google today supports around 120 languages. Until like 6 months ago, it supported only 80 languages. So think about this is around less than 1.5% of the world languages, not the world population, but the world languages. So that's a big problem. And of course, one of the most important problems is scale. And one of the issues is that with these algorithms, that they require huge amount of CPUs. And because of that, we really need to take into consideration how to optimize them. And when I'm talking about how to optimize them, is meaning how to make them much more efficient, and also how to make sure that they are really low latency. Because imagine, even if I had the most amazing algorithm in the world, okay, that understand everything that I'm saying, but it takes 20 minutes the system to understand what I'm saying, and nobody cares about that. So I think that these are the major challenges, and luckily for me, this is a really interesting topic, and there are a lot of other interesting things to work in the future. Thanks.
Are there any questions? Yeah.
Hi. I would like to hear your prediction on which one of the two models you presented, attention one or LSTM-based models, will be leveraged and will have the advantage in the future.
Basically, so attention models is in
speech recognition and text classification.
So in speech recognition, usually attention models are not being used mostly today because sometimes it's really hard to implement them. There are some work on attention models, but they are not really popular, and they're not giving a lot of improvement. In terms of text, a lot of the papers that I see today are based on memory networks and attention models, and basically LSTMs is some kind of deduction of some kind of more generalized of memory network and attention models.
Okay, thank you.
Thank you very much.